Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Dr. Rudrashis Majumder. Rudrashis received his master's degree in Control Systems Engineering from Jadavpur University, Kolkata, India in 2016. He later pursued his PhD in Aerospace Engineering at the prestigious Indian Institute of Science IISC, Belgaru in India, completing in 2022. Currently, Dr. Majumder serves as a postdoctoral research consultant with ARTPARK, AI and Robotics Technology Park, a collaborative initiative at IISC aimed at fostering cutting-edge research and development in AI and robotics. His work involves the development and application of advanced machine learning algorithms, control systems, and game theoretic models for enhancing the path planning, control, and decision-making process of autonomous systems. His research bridges theoretical insights and practical applications, addressing critical challenges in real-time autonomy and multi-agent coordination. Rudrashis, thank you so much for joining us this week. And with this short introduction, you can start whenever you're ready.
Yeah, thanks, Johan. Thanks for the nice introduction. So today I'll be presenting my work, Physics-Informed Neural Networks for Safe Navigation of Autonomous Vehicles. We call it PiSNAV algorithm. So hello, everyone. I am Dr. Rudrashis Majumder. I am working in ARTPARK. And thanks to Professor George for inviting me for this talk. So to start with, so I'll first tell the outline of the talk. I'll introduce the problem. I'll talk about motivation challenges, then a bit of overview. Then I'll talk briefly about sensing and perception because it will give some glimpse of how things are being controlled in the particular work. Then comes safety in robotics, how we define safety in our work. Then comes obstacle avoidance with PIN. Effectively, that is PiSNAV algorithm. Then case studies with static and dynamic obstacles. There will be some comparative studies. Finally, I conclude my talk with hardware experiments, which will first tell the experimental setup, and I'll show you some videos of our results. Okay. So why do we need safety in robotics? So in real-world applications, we have seen that autonomous vehicles work in complex and dynamic traffic environments, so safety and reliability should be ensured because of in order to ensure the mission success. Then comes industrial automation, where the robots work in factories and warehouses. Then comes search and rescue, where we use robots, ground robots, aerial robots, or underwater robots to navigate through disaster zones, gather information, and locate survivors. Finally, exploration and surveillance, where drones and robots are used to explore unknown area, such as underwater or in space. So what do we mean by safety in our work? Particularly in our work, when we talk about safety, we want to refer to it as preventing collisions with humans, objects, or any other robots. To ensure safe operation in various environments, we need certain policies and protocols to be inbuilt into the robot computer system. It is needed to increase the efficiency so that the robot is enabled to navigate smoothly and efficiently without getting stuck or getting collided to some objects. And also optimizing the robot paths for time and energy efficiency. So if I don't show this slide, then also it is not very difficult to understand that robot obstacle avoidance is very crucial for enabling robots to operate safely and effectively in real-world scenarios. Okay, so when we talk about obstacle avoidance or safety in our work, there are certain challenges like dynamic environments, where we get moving obstacles in the scenario, and we don't every time we don't know that how it is moving and all. Then there will be some unpredictable changes in the scenarios, like some robots can become rogue. It can start moving very quickly and in a very unpredictable fashion. Then there are some computational constraints where real-time processing is important, and the robot should have that kind of computational resources carrying inside it. Other challenges are uncertain and complex environments, varying obstacle shapes and sizes, and sensor failures, or some other unexpected events. So to summarize these and to address this challenge when we are doing this particular work, we'll be talking on a novel formulation of obstacle avoidance problem with physics-informed neural networks. We call that as PiSNAV algorithm. We'll talk about control barrier function to avoid obstacles for safety guarantees. Control barrier function is a mathematical policy which can guarantee safety in certain environments. So we use the advantage of it. When we talk about control barrier function, there comes quadratic programming into picture, where control barrier function forms the constraints in the optimization. Then we convert the quadratic programming problem or optimization problem into Hamilton-Jacobi-Bellman equation, which is actually a actually a partial differential equation. So this Hamilton-Jacobi equation is solved by the PiSNAV algorithm, and it gives the optimal maneuvering input to the autonomous vehicle. So in a bigger picture, if we see the autonomous vehicle system, it is something like this. It has some actuators, some sensors. Sensors are like lidar, radar, sonar, etc., which can sense whether there is any object or obstacle in the environment. So the sensor tells the decision-making system or flight controller unit or a robot controller unit that whether there is a potential obstacle or not. If there is no obstacle, then we use a proportional integral derivative controller so that the robot can track the predefined trajectory or path and reach the goal or destination. If there is an obstacle, then we use the PiSNAV algorithm. And according to that, the control input is generated, and that input tells the actuator like propellers, motors, control surfaces to act accordingly so that the autonomous vehicle can take optimal and efficient maneuver. Okay. So to sense whether there is any obstacle or object in the system and to have the perception about it, we can't deny the importance of sensors. So robots need to accurately perceive their environment, whether there are obstacles, whether it is static or dynamic. The quality of the obstacle avoidance depends on heavily on the quality of the sensor data. Then environment representation should be good enough for the robot. There are certain things called occupancy grids, where the environment is divided in different grid cells, and each cell is marked as occupied or free. Something is called point clouds, where we get the representation of the environment as a collection of 2D or 3D points. And there is something called feature maps, which extract relevant features from the sensor data, such as edges, corners, objects, etc. So these are some representative figures where you can see that the real world environment, which is a maze kind of scenario, can be extracted as a feature like this, occupancy grid map like this, and this is a point cloud representation of some object or obstacle. Okay. There are different types of sensors used in our work. One is range sensors. There are certain variation of the sensors like lidar, ultrasonic sensors, radar, infrared sensors. Then comes the vision-based sensors like camera, depth cameras, and stereo cameras. So with these, the first part of the problem is solved, that is sensing the object or obstacle and then having the perception about it. After that, there is a decision making. So what is safety in our work? As I told, the safety is the collision avoidance or obstacle avoidance. A critical aspect of safety in robotics and unmanned systems is always in discussion. It involves a combination of sensing, perception, planning, and then control. So when we want to see the picture in a schematic fashion, we see that this is the vehicle which has a sensor inbuilt, or it is added to the system like that. Then when it senses the object, then there is a perception unit. After that, there is a decision-making block which decides whether we should consider it as a potential object or not. potential obstacle or not. If there is an obstacle, then there is a chance of collision, so that should be eliminated. So then flight controller takes the decision that how the control policy of the particular autonomous vehicle should be designed. After that, the control and stabilization aspects are taken care of. Then all these control input strategies go to the actuation block. And finally, the actuation units like propeller, of the propellers function in a specific way so that the drone can take a specific turn to avoid the obstacles present in the environment. It can be static, it can be dynamic, and also it can be some other drones or other robots in the environment. Okay. Now, as I told, that control barrier function is the algorithm which we are using for obstacle avoidance. Then, okay, it is a function that control the autonomous vehicle safety by defining barriers. The barrier divides safety in such a way that the barrier divides the regions as safe and unsafe regions for the autonomous vehicle. I'll give one example like this. Just assume that you are flying kites on the terrace. So what is the safe region and what is the unsafe region? The safe region is on the terrace. And if suddenly, without being mindful, you fall down from the terrace, then it becomes unsafe. So what is the barrier? Barrier is the parapet wall, which actually tells that inside that parapet wall, the region is safe for the kid who is flying the kite. And outside the barrier or parapet wall, it is unsafe. So this is the basic concept of control barrier function. In robotics, when we talk about unsafe region, that is obstacle or other autonomous vehicles. And when it is safe region, it is the area excluding the obstacles. That means when a drone is flying in the environment and there is a building, then the building is the unsafe region for the drone. And outside building, whatever free space is available is the safe region for the drone. So control barrier function is a function depending on the states of the vehicle. And it is defined in, it can be defined in different terms, but here we are defining it in terms of distance. What is happening here? There is one image. You see that this is a drone which comes, encounters one obstacle here. So we create a safety barrier around the obstacle, and this particular distance is the distance r. Okay, so what is the control barrier function? Control barrier function is the distance between this drone. Just consider the center point of the drone and the center point of the obstacle. That distance, square of that distance is represented by this particular term, minus r square, this term. Now you see that for safety, this particular distance, that means this orange line, this distance should be positive for safety. And if this particular drone crosses this barrier, then the collision is inevitable. So at that point of time, the control barrier function becomes negative. So if we want to summarize these, then control barrier function is a function that defines safety by setting up barriers between safe and unsafe region. If it is safe, then the control barrier function should be positive. If it is unsafe, then it should be negative. To see a pictorial view of how control barrier function will be decided in case of robotics is something like this. The drone comes in the environment and it encounters one no-fly zone or obstacle or unsafe set. So through its sensor, it maps the points on the boundary of the unsafe set. Now, the drone itself has a turning capability. It can't come very close to the red points and then start turning, because then that will not be a maneuver which will be a successful maneuver and collision will happen. So based on the turning capability of the drone, there will be some safe points which will form a kind of locus in the system, and we can tell that the drone should not cross these points. If it crosses these points, then it will not be able to turn sufficiently, and though it will be aware of the presence of the obstacle, it will not be able to avoid it. So these are some safe sample points we talk about. Till this point, it is safe to maneuver without collision and unsafe beyond this. Assume that these are the leader rays, And these are the unsafe sample points, as I have told. So coming to this particular point is, of course, the collision, but depending on the physical dimension of the drone, its turning capability, it is also mandatory that the drone doesn't cross these safety points. So this no-fly zone or unsafe zone is characterized by the control barrier function, which becomes negative. Okay. Now, when we have the control barrier function in our hand, then we, in general, how the problems are solved in robotics is that we'll have the control barrier function. Based on that, we'll create a constraint, and that constraint will serve as a constraint in a optimization problem, which is a quadratic programming problem. So for quadratic programming problem, the objective function is quadratic, constraints should be linear. So in general, energy consumption optimization is considered, and energy minimization problem for obstacle avoidance is considered here. So the objective function is to minimize the energy subject to the state equation of the system or the autonomous vehicle or drone or robot. I can use these terms interchangeably. And this particular constraint is the control barrier function based constraint. So we need to solve this particular quadratic programming problem. We get the U, which is the control input, that minimizes this particular objective function. And in order to maneuver in a minimum energy consumption way, that particular U should be utilized by the autonomous vehicle. X is the state vector, U is the input vector, and the control barrier function is already defined in the previous slides. So it is something based on the distance. There can be angle-based control barrier functions also, but in this particular one, we are not considering. The concept of control barrier function and quadratic programming problem, to solve that, was first conceptualized in this particular paper, 2016, by ARTPARK. Okay, now up to this, the problem is very straightforward. We know that there are some obstacles in the environment, and we go through control barrier function to create the constraints, which will enable the drone to obey the safe and unsafe region and the boundary. But after that, what we do in our work is that from the optimization problem which we encountered in this particular slide, we convert this optimization problem into a Hamilton-Jacobi-Bellman equation, which is essentially a partial differential equation. Why we do that? What is the advantage? When we do that, it will be clear in the later slides. So Hamilton-Jacobi-Bellman equation is a PDE. It plays a central role in optimal control theory. It provides necessary and sufficient condition for optimality in continuous time dynamic systems. It helps finding the best control strategy to minimize something. For our case, it is the energy. Now, when we break down the problem, then we first get the optimal control problem that we have got in the previous slide, the optimization problem. Then there is a value function involved. Out of that, we formulate the Hamilton-Jacobi-Bellman equation. Then we solve it using physics-informed neural network. Solving optimal control problem with Hamilton-Jacobi-Bellman equation and then solving it with physics-informed neural network was first conceptualized by this particular paper. At least I have got this paper, which have talked about optimal control systems, closed loop guidance and control in aerospace systems using PIN. So the important application becomes designing optimal controllers for robot motion planning and control. And we use this idea to convert the particular optimization problem into something which can be solved by physics-informed neural networks. There are lots of advantages which I will show in the result section. Okay, so what is our Hamilton-Jacobi-Bellman equation? The formulation, mathematical formulation is given in this particular paper by us. I am not going into the detailed derivation, but I'll give that in which flow the problem is formulated. So first we have the system equation, that is the dynamic equation or kinematic equation of the autonomous vehicles. Then we have the control barrier function. For that, we have a control barrier function based constraint, which is a very standard thing given in ARTPARK paper, When we have all these, we get the quadratic programming problem. Now, if we don't go into all these steps and just solve the quadratic programming problem by some solver, then also we get the optimal control input U, which will minimize this particular objective function. But what we are doing here is that we are defining a value function. Based on that, we get a Hamilton-Jacobi-Bellman equation. And finally, we solve it for the optimal control input and get a final PD for a point mass model. We started with a point mass model to gain some confidence into the particular algorithm. And then we started increasing the complexity of the model. So here, what we get as a final PD is a point mass model. Okay. Now, in this particular work, we create a network where the input is the states of the model and obstacle information. What are the states of the model? This is X and Y. When it's a point mass model, it has X position and Y position as the state vectors. Then there are two hidden layers with 100 neurons. There are activation functions used for these neurons. And what we finally get is the optimal value function V. Now, the pin learns the optimal value function V. From that, it derives the optimal control input U star, which minimizes the loss function. And this U star is used by the flight controller. It guides the actuator to implement this particular U star, and then the vehicle takes sufficient maneuver so that the obstacle is avoided. And also, if there is a collision, probable collision with some dynamic objects like human being or something like that, that also can be avoided. Okay, so how do we train the model? Collocation points are generated, random x, y, theta. X is the x position of the vehicle, y is the y position, and theta is the heading. These points are generated using Latin hypercube sampling. It is something like this, if you see the right-hand side. The autonomous vehicle is the blue dot, and the red dots are the obstacles. These are the safety barrier. The green is the safety barrier, which the vehicle should essentially not cross. But if it crosses, then there is another barrier called near collision barrier, which should not be crossed at any cost. The black lines are current heading, and this red line is a heading towards the obstacle, which it needs to be avoided. The goal of Latin hypercube sampling is to ensure that the sample represents the full range of the input variable. That means it doesn't give importance to certain portions and miss other areas. So like that, the collocation points are generated. Then the obstacle information is given in the difference between theta and the heading towards the obstacle. And if I generate one particular scenario to show that how things are obeyed, it is something like this. The autonomous vehicle is in unsafe region because it has crossed the safety radius somehow because of its high linear velocity or something like that, or limited turning capability. So somehow it has crossed the particular safety barrier and has gone inside that, but it should not cross the pink barrier, that is the near collision barrier. These two barriers depend on the dimension of the autonomous vehicle. And when you see this one, this red line is the heading towards the particular obstacle, which should be avoided. So this del theta should increase. So in this way, the network is trained. The loss function is the PD, which is to be solved. We train the network for 8,000 epochs, learning rate of 2e minus 4, and we use Adam optimizer. And after training, we see that the network is learning the policies sufficiently and the loss is coming down. So with this particular model and some confidence with point mass model, with the mathematical formulation of the Hamilton-Jacobi-Bellman equation, then getting the PD, then training the network and getting the loss converging, we go for testing the results.
Can I ask a question, Rudrash?
Sure, sir. Yeah.
It seems that you have the constraints. These are sort of soft constraints, like in penalty, like in pins.
Yeah.
You didn't need to go to harder enforcement like augment Lagrangian or for.
So, sir, it was not required in enforcing that, but we had like when we have formulated the Hamilton-Jacobi-Bellman equation, then we have a Lagrange multiplier, and based on that, the PD is formulated. But we are not enforcing any condition based on that.
Right. So I'm asking if that is sufficient, because we found
Yes.
that going to augment Lagrangian formulation was better.
Okay.
We've done similar things.
Yes.
In
So
the SCIAM paper.
Sorry, sir. Some theoretical developments are still going on, but this is the initial phase of the work, and we have evolved from it. So this is the first phase when we started the work, and I'll show you some preliminary results, then I will talk about the model.
Okay.
So what we are essentially doing is that in the training phase, we first formulate the CBF, then formulate the quadratic programming problem, then formulate the Hamilton-Jacobi-Bellman equation, and finally we solve the Hamilton-Jacobi-Bellman equation with our algorithm, PiSNAV. So this happens in the training. Then when it comes to execution, then in hardware also, we see that there is a sensing unit. After that, we have a perception. Then there is a decision making. Then if there is no obstacle, then a proportional integral derivative controller is sufficient enough for sending the vehicle from the starting location to the destination. And based on that, the actuation will take place. But if there is an obstacle, which is a danger, then there will be optimal control input formulated by PiSNAV. And then that optimal input will go to the actuation unit, and finally the vehicle will manually. Okay. So these are some preliminary results on ground vehicles. We do experimental validation that considers a simple point mass model. And for point mass model, this is the kinematic equation. We see that with the PiSNAV algorithm, the vehicle is able to avoid multiple obstacles which have smooth boundaries in the area. Then we were curious to see that whether it is a special case, that's why it is happening, or there is some limitation in our algorithm where it will fail. So we were curious to see that what happens with the obstacles of sharp edges, and we got success there also. With this confidence, we went into a hardware implementation of the point mass model with a turtle bot. So the bot is placed in the area with the obstacle. The obstacle should be on the path of the turtle bot. Companion computer reads the LiDAR data, and then obstacle distance, obstacle coordinates, all these things are obtained. Then PiSNAV algorithm uses the LiDAR data. PiSNAV generates the velocity commands to control the bot, that is the U star. Then the spin generated velocity is sent to the controller. Based on that, the command goes to the motor, which is the actuator, and then finally the maneuver takes place. So you can see that there is a single obstacle scenario where the robot was moving in a straight line and suddenly it encounters an obstacle and then maneuvers. Then this is a multi-obstacle scenario. In this particular scenario, we don't have any proper goal location. It is just exploring and avoiding the obstacles. And that is what it is expected from the drone, sorry, from the vehicle. Then finally, we tested one random obstacle scenario where we drop the obstacle in front of the moving bot and it stops, it starts changing its heading. So when we talk about ground vehicles, we have the UI motion of the vehicle in the X and Y coordinate. But then after formulating the first problem in a point mass system, we wanted to see that what happens if there is a movement in the vertical direction. Yes.
Excuse me. Can I ask a question? I'm
Sure,
Kamal from Brown. In the previous slide,
yes.
when you put additional obstacle in a dynamic way, does it check like the minimum distance travel or the minimum time?
Is it the last case?
Yeah, last case.
Yeah, please ask me the question once again.
So is it check like what will be the minimum distance to travel or anything like minimum time to reach the destination?
Yeah, for this particular scenario, the dimensions are such that when it is dropped, it is sufficiently far in this particular scenario. But what happens if, okay, I'll show you some other simulations also where you will be seeing that if the velocity of the obstacle is too high, then there are certain problems. And that is very common in the robotic environment, because if the obstacle which it needs to avoid, that velocity is very high or it comes in a very close vicinity, then the turning capability of the robot might not be sufficient and collision might happen. But that is a special case. Is it answered, John?
Yeah, one more thing, you have a destination to reach. So how much
in this
time it will
particular,
take?
yeah.
Yes.
In this particular experiment, there is no destination fixed. We are just expecting that it will somehow explore this particular arena and it will move. And whenever some obstacle comes in picture, then it just avoids. So there is no particular goal location as of now.
It's just trying to avoid the obstacle.
Just trying to avoid the obstacle.
Okay.
That's why in this particular experiment, PID control also doesn't make sense, because we are not planning to send the robot to certain location. But in the next scenario, for other things, like when we have to track one predefined trajectory, then we need another additional controller, that is PID control.
Okay.
Yeah. So that effect will be seen in this particular results experiment. So here we take underwater vehicles, and this is also just a numerical simulation. AUV explores the maritime environment in the heave motion, that is a vertical motion. In the absence of the obstacles, depth is controlled using a conventional PID controller. But when the avoidance should be done, then onboard sensors tell the flight control, the vehicle controller that there are some obstacles in picture and it should be avoided. And to avoid the obstacles, they will deviate from the intended path by the help of PiSNAV algorithm. So you can see the first figure where the vehicle, the underwater vehicle starts from this particular position, starting position. The mission which it needs to conduct is that it should come down to a certain depth and then monitor the area. That is the plan. Now, it comes down. There is a predefined trajectory, which is the red one, the reference trajectory. And PID control helps the vehicle to come down, follow the trajectory, and move in a particular fashion. But what happens at this point, there is one obstacle. Then PiSNAV comes into picture. The pin trajectory is this green one. By doing this, it avoids the particular obstacle, then comes back to the PID trajectory, reference trajectory, and tracks the reference trajectory by the PID controller again. So it is a kind of switching control between PiSNAV and PID control. This is another scenario just to see that how fast the particular algorithm, the vehicle can adopt with PiSNAV algorithm. There are two obstacles in the same area, and it avoids both and also tracks the reference trajectory. Then we wanted to see that what happens if there is one uneven shaped obstacle, whether sometimes what happens if it is a convex obstacle, then it can be avoided in an easier way. But when it is uneven obstacles, then problems may arise. So in this scenario also, we see that PiSNAV is avoiding successfully. But since we don't have a hardware setup for underwater vehicle, we couldn't validate this particular thing in hardware experiments. So we came back to the ground vehicle thing and then went into making the particular vehicle model a bit complicated from point mass model. Now we check the results with unicycle models. This is the equation. This particular thing is the control barrier function, which I have mentioned earlier. Then CBF constraint is formulated. And finally, we formulate the PD to be solved. And in the environment, we keep multiple obstacles. So this is a ground vehicle simulation where the vehicle starts from this blue point. And this is the goal location, Juan. Now we have the goal and we want to send the vehicle from starting location to this point. Somewhere in this region, it should reach. Okay, not for all the obstacles I have shown the barrier because that makes the figure cluttered. So for this particular obstacle, this is the safety barrier, and then we have one near collision area. When we see the dotted lines, these dotted lines are PID control because starting from here, it needs to follow a reference trajectory and reach the goal location. But when it encounters the obstacles, then it starts deviating by PiSNAV. And this deviation happens whenever it encounters any obstacles. Finally, when there are no obstacles in the environment, like in the leader data, when it sees that no point clouds are seen for the obstacles, then it switches to the PID trajectory and reaches the goal point. Okay, so this is the unicycle model with PiSNAV algorithm for static obstacles. Then we show the results of the unicycle model with dynamic obstacles, which is like another level of complication. What we do here, we set the vehicle velocity as 1 meter per second, obstacle velocity as 0.5 meter per second. Obstacle radius is 1 meter, and this is the barrier radius. So the first figure shows the vehicle trajectory. Okay, let me tell that this obstacle 1, is moving in a simple harmonic motion. So the center of the obstacle can go from this point 4, 4 to 2, 6 and 6, 2. So first the vehicle starts moving and encounters this particular obstacle, avoids it. Then when it is moving here in this particular region, it encounters another obstacle which is moving in negative X direction. It avoids that also and reaches the goal. So what is happening here in the second figure, we see that the separation distance is always non-zero. That means the collision is not happening. The black line says that before this particular time, which is 14.57 seconds, it encounters only the blue obstacle, and after that it is of no interest. And after 14.5 second, it encounters the second obstacle. So it avoids that also successfully. If we see the video, you can feel the trajectory. The same control barrier function, the same Hamilton-Jacobi-Bellman equation, the same PD, the same PiSNAV algorithm is getting effective for dynamic obstacles as well.
But here you don't ensure that it will go to the target at the fastest possible time, right?
No, that is not the concern here, sir.
Yeah, okay.
But since we are optimizing the control input, that means it will not take unnecessary turns. If it is not required, it will not take a very sharp turn and very far away, it will not move.
Sure.
Yeah. Okay. Now, after we saw that it was working for static obstacle, dynamic obstacle, some confidence from hardware experiments were also there. We thought that it is a time to compare with other algorithms because PiSNAV, which is based on PIN, is working, but is it working better than other algorithms? That is something which we wanted to figure out. So first we took artificial potential field-based obstacle avoidance. We fixed one environment, which is a cluttered environment, and it is expected that the vehicle will start from this point and reach the goal location, and the environment is cluttered with multiple obstacles. They are not arranged in a straight line, they are not arranged in an even order, and these are some, so we tried this algorithm with a range of different values of artificial potential field with attractive gain and repulsive gain. But we see that for 100 Monte Carlo runs, we notice that there is a collision. Okay, then we thought that fine, APF can fail because of different reasons, because it has certain limitations, but control barrier function, which has a safety guarantee, whether that is working. So we are solving the control barrier function with Hamilton-Jacobi-Bellman equation and PIN, but we can solve the control barrier function or the quadratic programming problem by directly by a solver also. How that works? So we see that it is avoiding. Fine. Good. We see that control barrier function is only by solving the control barrier function, the vehicle is able to avoid the obstacles, and then it is also reaching the goal. So this is the time it is taking, 33.62 plus minus 0.37 seconds, and the distance traversed is around 10.51 meter. Then we compared the pin-based PiSNAV algorithm with one of our own work, which talks about deep reinforcement learning-based controller for autonomous navigation. We see that here we are using reinforcement learning with control barrier function with the same parameters. We see that in reinforcement learning, as it is expected, it is taking way higher time, 70.67 seconds, and it is traveling more distance also. Finally, in the same environment, we use PiSNAV algorithm. What is happening here? With the same parameters, we see there is a drastic change in time. That is 23.61 seconds is the travel time. Distance is also much less than RLCPF and a little less than control barrier function. And avoidance is happening in least time, traversing least path. So that is the conclusion, but we thought that this environment might not give all the intuitions which we can draw out of this particular experiment. So we changed the environment and we made it like this. It is a U-shaped obstacle. If you follow robotics literature, you will see that when it's a U-shaped kind of thing, going inside, it leads to getting stuck to the local minima for artificial potential field. So as expected, when we implemented APF with the same parameters, we see that the vehicle is moving, then it is coming here. And after that, it gets stuck into a loop and not being able to go out. That means we can say that APF is not successful in avoiding the obstacles, though it is not getting collided, but it is not reaching the goal. So mission success is questioned. Okay. We consider control barrier function. We see the same scenario that it gets stuck to local minimum. We compare with our own algorithm, RLCPF, we see that it gets stuck to local minimum. So even like it is worse, it is traveling a lot inside, which is energy consuming, but it is not reaching the goal. Whereas when we see PiSNAV, we see with the same parameter values, it is successfully avoiding. So that is the finding which tells us that, yeah, PiSNAV we can believe on. And in this kind of scenario where there is a trend that many algorithms get stuck, this is not getting stuck.
So Rudrashis, is this the only method that uses the Hamilton-Jacobi-Bellman equation?
Yes, sir. Yes.
I see. So this is basically what you're saying, right? If you solve this equation right, then
yes.
With of course the
correct, sir. So if you just see these two figures, right hand side, this is the control barrier function which is directly getting solved.
Yeah.
But the problem is that the quadratic programming problem is time consuming, and when it gets different obstacles, every time it encounters one obstacle, it needs to solve the quadratic programming problem. So the time is increasing in the previous slide. Okay. But here, when the obstacles are arranged in a very like specific way, it is getting stuck. But in case of PiSNAV, in the previous environment, if we see, it was, wait, let's go here. Since the network is being trained with how it will treat the obstacles, how it needs to formulate the control barrier function, how to solve and all. Being trained, the network takes less time to avoid the obstacles and reach the goal. So that is the success of PiSNAV. Yeah. Okay. So when we compared the PiSNAV algorithm with some state-of-the-art and very classic algorithms, which are like often used in robotic literature for obstacle avoidance, we see that PiSNAV is sometimes working better and sometimes it is working way better when the others are failing. Okay. So with that, now we go for a hardware experiment where we create the similar environment, what I was showing in the simulation. We create a 6x6 meter grid. We measure the area. It will not be visible. The markers are there to exactly plot the area here in the particular arena. Then we have a ground vehicle, which we use as a Volta robot. If you can see, it is just behind me, this Volta robot. It has this following dimension, then these controllers, then onboard computers. We use RP leader, which is a 2D leader. Since it is a 2D leader, we see the point clouds like this. You can see when it is 3D, the point cloud will become 3D, but being 2D leader, it will give something like a semicircle because of these cylindrical obstacles. Then wheel encoders are used for the Volta to provide the real odometry values, that means X and Y positions. Then point cloud of the obstacles, when it is found in the sensing range of the leader, it is considered as obstacle. And then finally, the vehicle solves the problem, which is the PiSNAV algorithm, and then avoids in real life. Yeah. So the first one is the animation, which shows that how the vehicle is moving from like in between the obstacles, which is the first. Okay, this caption is wrong. It's not a U-shaped environment, but it's a general cluttered environment. This is the top view. This is the side view. And here we plot it as a front camera view, where it can see the obstacles and then finally finds its path.
So the computation is done on a desktop, let's say on your laptop, and then
Yes.
the path is communicated to the vehicle, right?
No, no, no. It is like getting computed on.
The computation is done on board?
Yeah. It's on board computer.
Really? You have what kind of computer do you have?
Yeah. So if I go back, you see that we are using this particular onboard computer, which is Jetson Xavier NX. And it is like, in this particular environment, it is taking around, how much? Around 50 seconds or something like that to cover through the environment.
I see.
So the path is not communicated. The testing part or execution part is fully on.
So it cannot go really fast because then it will not have
That is the limitation of the bot also.
Yeah.
Like it can't go that fast compared to a drone or something like that. Currently, we are trying to formulate this problem with a drone model also. So
I thought NVIDIA has these new mini Blackwells that are extremely fast.
okay. Probably we can see the possibilities that how the results change.
For edge computing, yeah.
Then we have the similar scenario here, where you can see the same environment, like the U-shaped environment. It reaches the goal. So goal is marked as a region, not a particular point, specific point. So once it reaches that particular area, it is fine. We are satisfied that it has reached goal. Yeah. Okay.
It's a bit over like conservative. Because maybe the way you draw the CBF.
Yeah.
It's a little conservative. It turns way before the obstacle.
Yeah, that is happening because it is sensing way before, and yeah, then the radius is also there. So why the particular thing, like as you are telling that it is rotating much before, that is because the size of the boat. Based on that, the barriers are created and it is expected to obey all these barriers.
Yeah, better safe than sorry.
Yeah.
I had a
Oh.
small question. If
Yes. Yeah.
this
Yes.
is Varun from Round.
Okay.
So I was like
Yeah.
wondering if
Hello.
like the initial direction that you provide has an impact on the algorithm's performance.
Not in that way. The initial direction is provided to reach the goal, which is essentially a straight line. PID controller will help it to reach the goal in the straight line. So it is happening mostly when it sees any obstacle on its path, then it starts changing.
If I don't have a straight line to start off with, will it actually
Then the
still
scenarios
figure
will
out?
change. The scenarios might change, but we haven't studied all this because this is the simplest application where we need to send some in logistic application or something like that. We need to cover the shortest path also. So if we want to send the drone in different other paths, carved paths or something like that, then the purpose also should be clear.
Okay, so your objective is shortest path, not shortest
Yes,
time as
yes.
such. Okay. Okay, thanks.
When it is exploring certain areas, like as I was showing for underwater vehicles, it might need to explore different areas, monitor, collect data, then it might be required that it will take some other path, but that is not required.
Okay.
Right. Fine. I can go ahead, right? Okay. So I conclude my study and whatever we have done with physics-informed neural networks. So we check the feasibility of PiSNAV for obstacle avoidance of autonomous vehicles. As of now, we have tried for ground vehicles, UGV, and underwater vehicles, AUV. The proposed PiSNAV framework learns the control barrier function for collision avoidance. It generates adequate control input for avoiding obstacles safely. Then it solves the QP problem as Hamilton-Jacobi-Bellman equation, which is computationally less intensive. You have seen that it is taking less time than the other algorithms. And also it is never stuck in the local minimum. Okay, then PiSNAV is scalable to multiple obstacles, can handle dynamic obstacles, but there is a speed advantage which is required because if the dynamic obstacle is too fast, then as you have seen that the robot is not a very high-speed vehicle, so there might be some problem which we haven't tested, but from the intuition we can tell that collision might happen there. There are some upcoming works like incorporating PiSNAV for UAV obstacle avoidance and then also incorporating time-varying control barrier function to handle dynamic obstacles. So as of now, the control barrier function is not a time-varying one. We are formulating it based on only distance, but we have a plan to extend the work in this direction. There are a few collaborators, Professor Suresh Sundaram from IISc, he is my postdoc supervisor. Then I have Bharatwaj with me, he is online. If some of the questions I can't ask, he can answer because he was a very close associate with me in this particular work. Then we have Hemant and Siddharth. Hemant was from IIT BHU. He did his internship in our lab and Siddharth was a research assistant. So with this, I thank all of you for your attention and I think the floor is now open for questions. So whatever questions you have, any suggestions, everything is welcome.
Thank you so much, Rudrashis. That was a really nice talk.
Thank you. Thank
Do
you.
we have any questions from the audience?
Hi, can I have a question?
Sure.
Please.
Yeah, this is Jacob. I'm from Carnegie Mellon University.
Hi, Jacob. Yeah.
For the great
Thanks.
talk, it's very impressive results, and I have two quick questions. So the first is that you mentioned that maybe you can go back to your HJB equation slides. Like you mentioned that you solve a HJB with the control barrier function constraints. Like
Yes.
as far as I know, those HJB equations that usually have those like a sup or like max operator in the equation, which makes it a little bit tricky than some other equations. How did you deal with that? Because I didn't see any like sup or max in your
Yeah,
equation.
so yeah, I agree with you. We are still trying to develop a few things theoretically. So we are exploring things, and probably like in near future we'll be able to answer. But as of now, this is the setup which we followed, and it is giving some impressive results. And we are analyzing a bit on, like, our focus is now, immediate focus is in implementing it in aerial vehicle models.
Okay,
But
okay, gotcha.
yeah, thanks for the suggestion. I think it will be nice if you can write to me also. Then probably we
Okay,
can
yeah,
think
sure.
together.
I'll
And
probably just talk offline later.
yeah,
And like another quick question is that like you
Yeah.
used pins in the framework. Like, what is the like the training data for that? Or like, did you just do a pure unsupervised training with only the physics laws, or they're actually training data to help with your training?
can you please come again?
Sorry, like I was just asking for your pins to work. Did you use training data? Like, if so, how did you generate it? Like, how dense was it imposed during training, or did you just do a purely unsupervised training with the physics
No,
laws?
it's kind of supervised, and
Okay,
we are
so
focusing on the physics also.
gotcha, gotcha. So did you train on different scenarios, or you actually generate data in prior for the fixed
Yeah.
scenario?
Probably some suggestions are welcome, that how we can like what we have started with, we have got these results, but how we can like complicate the scenarios and
Rudrashis, I think that the question is like, do you have when you have your laws, do you have loss of data, or you only have like
no,
boundaries
we
and
have only
equations?
physics laws. We
Okay.
have only physics laws.
Only physics laws. Gotcha, gotcha.
Yeah.
Interesting. And you mentioned that you actually generalized to different scenarios. Did you train on multiple scenarios with different physics, like optical
So
information?
we have generated around 10,000 of collocation points. And based on that, since we have used Latin hypercube sampling, then it takes the data in a very distributed fashion. So the training in that way with 10,000 collocation points becomes enough at this particular scenario.
All right, gotcha, gotcha. I think we're running a bit late. I'll just stop here. Thank you.
Yeah, thanks.
Thank you so much, Rudrashis.
Maybe
we have.
hold on. Jerome is not here, I think, but Paula is here. Paula, do you have any questions? Or maybe Sanchin?
Yeah, hello. I can have I have some questions indeed for your model of the vehicles or the robotics. So I see you model this by a point mass, but
Okay.
indeed if you consider vehicle, it have some geometrical shape, and the control must have some constraint that you cannot turn directly to like 90 degree or 180 degrees. So how you do with this kind of control constraints?
Can you point the slides while you have the question?
No, I
I am
mean
just-
when you do the modeling for your vehicles, I think you model by a point mass.
Yeah, okay. Let me go
Yes,
there.
and the dynamic is like x dot equal to u. Yes, here.
Yes, yeah.
So indeed, if you consider a vehicle, if you cannot like turn directly to 90 degrees, right?
So when there is a point mass model, then the advantage is that there is no like limitation in turning capability. It can turn anytime. But when it's a physical model, like unicycle model and all, then it becomes another challenge. Like as I was telling that we are adding the complications on the model. So when we go to the unicycle model, that is the challenge, that it can't turn as soon as possible. That in the hardware experiment, I have shown that some obstacle is dropped in front of the bot, suddenly it stops and turns. Okay, that might not happen in the case of unicycle model. So some speed advantage and all these things are.
Yes. Okay. I just because normally in the robotics, people can model it by instead of the Euclidean space, you can model it in a Lie group. So that states and the controls are indeed in a matrix space.
Yeah.
which models the angles and the tones. I don't know if you are okay. Never mind. Okay. So thank you for your clarifications.
Yeah, maybe we should move to the second talk because I think that Andreas is already here. Rudrashis, thank you so much for your wonderful presentation, and thank you so much for staying.
Thanks, George. Thanks.
Andreas, you are here.
Thanks, Professor
Are you
George.
here?
Thank you very much, Andreas. Very interesting.
Thank you.
So, hello everyone. Our second speaker for today is Andreas Radler. Andreas did his education and professional life in Johannes Kepler University in Linz from 2021 to now. He worked in Amazon Search from 2019 to 2021, and he was in ETH Search from 2016 to 2019. Andreas, with this short introduction, the floor is yours. Thank you so much for joining us this night.
Thank you for the invitation. Yes, I will present basically two papers that we worked on for the past 1.5 years roughly, which is called Geometry Informed Neural Network, which is like the main work, and then another paper that was a follow-up. My supervisor is Johannes Brandstetter, or as Johannes Brandstetter and Sepp Hochreiter. I think Johannes Brandstetter even told me he even joined the Crunch seminar 2 weeks ago by coincidence. Yeah, so maybe you still remember him. Yeah, I would like to start with a thank you to my collaborators and supervisors, especially Arthur Berzins, who was a great collaborator and supervisor on the journey, Eric Volkmann, Johannes Brandstetter, and Sepp Buchreiter. So this is the contents table. First, I would talk about geometry-informed neural networks, giving a motivation, and then basically answer the 3 central questions for this work, like how to present shapes, how to enforce constraints, and how to introduce diversity. After having done this, we then go to like an instance of this GIN framework, geometry-informed neural networks, which is generative topology optimization with a rather quick motivation, approach, and results. So this is like a smaller part. And then we will finish with some conclusions. All right, geometry-informed neural networks. So the main motivation is that in engineering applications, often we have little or no data available, but formal problem descriptions exist, and we would like to leverage them. So imagine for this example, we have, so this is not a shape that we want to optimize, but it's like a design region. So you can imagine this is the kind of like the design region that a shape shall be in. And for example, this green round thingies here are like the interfaces where a shape should attach to. We will see later more examples to this. But these are like formal problem descriptions, and we would like to leverage them. And so the central question of geometry-informed neural networks was, is it possible to train a shape generative model on objective and constraints alone without relying on any data? And there is really an analogy also to pins here. So I would kind of like start directly with the differentiation between GINs and generative GINs. But so imagine again, you have like, this is the design region with interfaces, and we also impose a constraint that the shape shall be connected. And additionally, we also can impose other constraints, for example, smoothness. So if we just train for a single solution, then we obtain, you know, such a result. So this includes the constraint of smoothness. But then when we want to obtain diverse solutions, we can also add a diversity constraint. And as you can see here, funnily enough, this is also leads also to a structured latent space. So there is, or modulation space. So basically there are 2 dimensions that parameterize different shapes. And when we interpolate here, or like move in the modulation space, also the shape moves or changes accordingly. Okay, so with chins, we have really three central questions. So how to represent the shapes. So there we are in this regime of neural fields of implicit neural surface, implicit neural shapes. And chins and pins can also be viewed in that aspect, but also conditional neural fields that we have in generative modeling. How to enforce the constraints? There we are like in this theory-informed learning regime, where we would see that Boltzmann generators and also pins are in here. And then how to introduce diversity. This is like with this generative modeling part. We also have this in Boltzmann generators, conditional neural fields, and generative chins lie at the intersection here. Maybe I guess a small differentiation. So I would say the main difference, although this is somewhat vague, but you could see chins as an instance of pins, I think, if you just go for this single solution. But then usually for pins, I think there is some work, but usually with pins, you don't go for multiple solution or like explicitly want to have near optimal multiple solutions. And this is kind of like what sets it apart from pins and goes into this generative chin regime. So how to represent shapes. So now kind of like we dive into the more like this computer graphics, computer vision kind of concepts. So we start with neural fields. Sorry, this should be an animation here. Yeah. So most of you are probably familiar with it. So a field is a quantity defined for all spatial and temporal coordinates. A neural field is a neural network or the field is represented by a neural network. And it is quite memory efficient because it compresses basically the underlying data, and it's continuous and differentiable. So I again start this video. This is from a paper called Instant NGP. It's very famous. And so, for example, here, they have a big image. When we just look at the left part, there is a big image, and they overfit the neural field to this image. Basically, it maps this two-dimensional domain to RGB values. And this is, for example, in the shape, which is more like our regime. But then, yeah, as we can see, it's like it also produces high quality and nice looking shapes or visualizations. Then we come to implicit shapes. So for those of you who are not so familiar with it, there are different ways how to present shapes. And one of them is implicitly by using a function. So maybe if you just have a look at this bunny here, then one could say that if I take if I define a function, and I could say if this function should represent this bunny, then I want the function to have the value 0 if we are on the boundary of this bunny. And then if we are inside, the value should be negative, and if you're outside, the value should be positive. And for a signed distance function, so the sign comes from this like negative and positive part, and the distance function basically tells us, we want to have the distance to the closest boundary point. So let's say here there is a smaller negative value than further down, further up here. And here this is like the biggest value probably is here in the corner. So we have a function. Yeah, and please interrupt me if this was not clear. I think it's not super important to understand the rest of the talk, but we can also take the time, I think. Yes, so for the function, so we have a function that maps from the domain to the real numbers. The boundary is defined as the set of points where the function value is 0. This can also be generalized to say this could be any level set. In the simplest case, it's just a 0 level set, and then we have a proper signed distance function, but it could be any other level set too. And the shape is basically then the set of points that are smaller than 0, so that are really inside this boundary. So these are like signed distance functions. And then a neural SDF is then if we parameterize this function with a neural network. So there are like neural fields and there are conditional neural fields. we have, like when we look at this here on the left-hand side, we know if f of x just represents a single shape. So imagine that we have 3 input coordinates for this car, as it lives in 3 dimensions. The output is just this signed distance value, and then this represents the shape for us. But now we can make this conditional and represent multiple solutions. So we have again like these 3 input coordinates, which define like really the coordinates of the point that we want to evaluate. And these other 4 points here then are like modulate different solutions. So this is kind of like a GIF. If we change this in here, we can see that also the shape here changes. So we can modulate different, like a whole set of shapes. Okay, then to the second question, how to enforce constraints. So this brings us into the realm of theory-informed learning. It uses scientific knowledge to eliminate inconsistent predictions and reduces the reliance on data, which can be driven to a data-free extreme. I think you, in this crunch seminar, you're very familiar with pins. And so, of course, pins are like a very prominent example for theory-informed learning, but we kind of like framed it in this more general umbrella term of theory-informed learning. And how do we come now from constraints to losses? If we start with a set of constraints, we relax these constraints into differentiable losses and solve an unconstrained optimization problem. So let's take a look at this example again here. We have a design region, so it should really be within this box, or like this box defined by the mesh, so to say, or like this shape, defined by the mesh. So we want the shape omega to be contained within this design region epsilon. And then we say, you know, how can we make this to a function constraint? It basically means that for all points outside of this design region, the function f of x should be greater than 0. So that means there is no shape that is really outside. I hope this kind of like intuitively makes sense. And then, so this is like the function constraint on the signed distance function. And then the loss for this is, you know, if we sample different points outside, and if there is a point negative, which means there would be a shape, then we want to penalize this and actually make it positive. Similarly, for the interface, we want the boundary of the shape attached to these interfaces. And so we want to enforce that the function value at these interface points are 0. And we can also directly enforce this with the loss. So there are like different ways, like different losses or different constraints, and I think we have an overall up to 6 or 7 constraints that we formulate and then optimize for. So one important constraint was also the connectedness constraint. And some of you might be familiar with Moore's theory. I'm definitely not an expert on this, but we digged somewhat into it during this work. And one observation or one result of Moore's theory is that the topology of a sub-level set changes at critical points. So when we have this as a signed distance function and we increase the level set, when we change the level set, so to say, suddenly, you know, these two disconnected components, they merge together to one. Also, similarly, the topology changes here, so there is like a hole, and then at this critical point, at this critical point, the topology changes, and also with this example. And just for you to kind of like get an intuition, for example, if we now would like to form a single connected component out of these two shapes at a certain level set, let's say it's here, at this level set here, then we would have to push the function value down. So we would have to change our neural network weights in such a way that the value at this point kind of like moves down. And then we can connect these two shapes up. So this was more like the intuition part. There is a very nice mathematical tool, which has also many implementations, which is persistent homology. It is a tool to analyze any like the Betti numbers via a persistence diagram. And we can really analyze any Betti number, whereas the Betti number is like the wholes of order n, the nth Betti number. And so the zeroth Betti number is just the number of connected components. And it does analysis of, when do certain topological objects, like connected components, appear and disappear if we change the level set. And this can then be like plotted in such a birth time and death time diagram. And we can then kind of like penalize these points to move them around. And in this way, put the topological properties that we want. Okay, then we have, like with this framework that we introduced, we have several, let's say, validation examples, simpler examples for a single shape, which is, for example, this minimal surface. We optimized zero mean curvature and interface constraints here, and we obtained this shape. It's really rather simple. Then also a parabolic mirror that collects the rays and the points. And this one is already somewhat more interesting because it attaches to interfaces at the left and at the right. It is within a design region. And when we enforce this connectedness constraint, then also the shape connects. And we really see that, if we don't enforce this connectedness constraint, then the shapes are also not connected. Our most like our biggest experiments is on 3D, where we optimize this jet engine bracket that you already saw before. And so now if we add one constraint after the other, then we can see how these shapes become better and nicer over with more constraints. So if we just put the design region constraint, then we can see that there are some blobs in this design region, but the constraint is fulfilled. Like it's fulfilled, but it's not very useful. When we then add an interface constraint, then we already see that the shape looks more like as something that is actually like a jet engine bracket. Then when we add connectedness, it looks better, but it's too wavy. And then with the smoothness constraint, it really looks as something that could be a mechanical engineering part. So this is like an animation how a single shape is trained. So up to 4,000 iterations. I think this takes roughly 10 minutes or so to train on a small GPU. Like I think it needs 1 to 2 gigabytes of VRAM, but that's enough. Yes, and now kind of like what we tried out was kind of like what happens now, like without any diversity constraint or something. What happens now if we just use the constraints that we had before, just the geometric constraints. Sorry, just the geometric constraints, and make it with a conditional neural field. So we put in, so to say, coordinates and modulation, and predict learn the shapes. And we really see that this suffers from mode collapse. So this is an animation that interpolates in this modulation space, and we see that the shape somewhat changes, but it doesn't really move to the other side. And this can then be mitigated by a diversity constraint. So how to introduce a diversity? This was extremely interesting for us because we started with some smaller experiments just on this horseshoe example. And there's some very nice literature on this, entropy and diversity from Tom Leinster. I can really recommend it. It's a great read. He and prior works also mathematically rigorously derived like how to measure diversity. And diversity, which we denote as delta of a set S, is its aggregate dissimilarity. And there are like two functions to aggregate dissimilarities that we tried out. So for dissimilarity, you can think of it as like as a distance function, but often the triangle inequality or symmetry doesn't really hold. Yes, so we tried these two functions. So here it's like there is the distance. This was just the Euclidean. Okay, so I just explained the problem maybe first. So the domain is such a horseshoe, and we start with many points. We sample like 1,000 points, and then we want to optimize these points to be contained within the horseshoe, but also to be diversely distributed over this horseshoe. And we tried different variants, and we can see that some variants did not succeed because the points were pushed to the boundary, and some were really, these two succeeded very nicely. So so we can think of this this constraint as kind of like you look for the closest neighbor of point, and you want to increase the distance to this neighbor. I often I imagine it's something like as particles in a room, which are like repelled from the neighboring particles, like they bounce against the neighboring particles, and this way kind of like you get a more or less evenly distributed distribution over the space. What we could also see is that like let's say if we just compare it with this one here, if we take not the minimum distance, like the closest neighbor that we repel from, but if we take like the that we want to repel from all other neighbors, then this doesn't really work because basically far away points get also quite a high penalty, and then basically it means that we push those points just as far away as possible. We can see that the points are only on the outer boundary of the horseshoe, not on the inner boundary.
Andreas, it
Yeah.
seems to me that for this particular example, if you use the curvature, then you will get the picture that you have for p equals 0.5 or 1, because it's
Sorry,
really
it's
really, look at the curvature there, that it increases, and because of the endpoints, and that's where you're gonna populate this.
You mean here in this part?
Yeah. So it's driven by the curvature.
Yeah.
Because that's the sharpest curvature that you have in the entire domain. Everywhere else, the curvature is uniform. So that's why you have this uniform distribution, but it's really curvature driven, the whole thing.
True. Interesting observation, actually. Yeah, true. Yeah, I mean, it's like I think this is an extremely interesting research topic. I think there's still a lot to be done there to understand this better, and probably like from how Leinster defined it, the diversity like from his literature we could derive a somewhat different diversity constraint. But we tried it out, and empirically this still kind of like worked better. But also we did not really thoroughly experiment with it. It was just initial experiments that we didn't really add them as ablations, let's say. But what is also interesting, like when we push the closest neighbor away, we also see that this like concavity is important. So like on this axis, basically we it's like the pushing the closest away, or like pushing like the mean or the sum away. Here it's like the concavity of this P is important. Basically meaning that if it's for the loss, it makes more sense, so to say, to push closer points farther away than already far points farther away. And so therefore, like the P is if you wanted to make it concave, P needs to be smaller equals to 1. And here we can really see that this works, and for P is equal to, it does not work. Yes, and then we applied this constraint, and it really surprisingly led to a structured latent space. So there's also, I mean, there are some caveats to this. This does not just like there are some nuances on this. So for example, usually it makes sense to kind of like the shapes should not start too differently from each other, and that the model itself kind of like learns to push them apart via the optimization procedure. If they start very differently, then this does not really lead to a structured latent space. But yes, if we start small, like if these shapes are very similar, then this works out really to our surprise. So we have this jet engine bracket example where the mass is moved forward and backward, And we also had this example of a 2D wheel that looks a little bit like ananas slices, or like, sorry, pineapple slices. Yes, but we also see that this kind of like is diverse and structured. Yeah, so what were our learnings? Training a shape generative model purely from objective constraints works, but the problem was somehow that the shapes are not really mechanically useful, and we address this by our follow-up work, which I will come to now. So the next paper is generative topology optimization. And just maybe a quick introduction to what is topology optimization. It is a family of methods to find near optimal geometries. And the goal is to, like in naive terms, to just maximize stiffness subject to volume constraints. So if we look at this animation here, there is again a design region. Probably there's a force applied here at the top, and then you try to find a shape that kind of like is maximally stiff, or like by still kind of like having a certain volume. And this is kind of like described by these constraints. I will not go into detail here. I think they don't matter too much. But this is computed by finite element methods. So what is our motivation behind this? The problem with classical TO, with most methods of TO, that they usually produce only a single shape. But multiple diverse solutions are desired because, you know, often aesthetics or manufacturability are hard to define and hence to optimize for. So, you know, give me a loss function for making something beautiful. It's somewhat hard. Maybe smoothness is a good like it goes into the right direction. Most people like prefer smooth shapes, but it's just really hard to define. And so basically the motivation is to, if we produce many different results, maybe a practitioner can select the best one that is best looking or easiest to manufacture. And so the central question we asked was how to obtain diverse, near optimal solutions to a given topology optimization problem. The approach we took was we used a finite element solver in the loop to obtain stiffness gradients, and also added a diversity constraint based on the chamfer discrepancy. So this is like the overall view of the method. So again, we have like a conditional neural field with coordinates modulation. We produce several different shapes. Now here we don't use a signed distance function representation, but we use a density representation. I think I spare you the details. It's similar, but it doesn't map to real numbers, but it maps to numbers between 0 and 1. And basically says, is there a shape or not? Gives you the density. If it's 0, then there is basically no shape. And then this is forward passed into finite element solver. We obtain compliance, or like these stiffness gradients and volume gradients. And also we have like this chamfer discrepancy with the diversity loss and obtain the gradients and optimize kind of like for diverse shapes. So we find that generative topology optimization is more diverse and also faster than prior work. So how should I say, since there is a finite element solver in the loop, we are somewhat constrained to smaller problems. So mostly 2D, we also did a 3D, which I show on the next slide. But therefore, please don't be confused to like why suddenly only 2D or mostly 2D results. So this is a shape where there's a force attached, like pulling down here and pulling down here. It's a rather classical topology optimization problem. And a baseline method produces two shapes which are diverse, also topologically diverse. And ours produces 9 shapes, and this in an even faster way. We see that our shapes are probably not as nice looking. Also, they are wavier. This comes from the neural field representation, as we use like a periodic activation function, not sine as in siren, but you might have heard of the wire architecture. And but we think this is not really a problem because post-processing can really smoothen this out. Yeah, and for the jet engine bracket, we also see that we can discover diverse modes. It's definitely less diverse than chins. but still diverse. And we think that the reason that it's less diverse than this classical chain stiffness is really more constraining than the connectedness. So to fulfill the connectedness constraints, the shapes really only have to be connected. But in order to be stiff, something close to the optimal shape would be good. And we can see that basically that here there's like a gap in between. There's also a gap in between, and these are then gradually filled up with these two other shapes. So yes, so these are some of the results we obtain. Then I come to the conclusions already. So some learnings I think that were interesting for me. That data-free shape generation works. This was not so clear when we started the project, but it really works. And also that the diversity is really a very useful constraint. And I think hopefully this will be explored and understood better in the future. From the future work, I think improving training speed, stability, and especially sample efficiency would be great. I think some second-order optimizer breakthroughs recently came out with pins, and maybe we can also directly transfer this to chins. Then I think on the diversity front, I think going to higher dimensional modulation spaces would be very interesting, because for now we just have experimented with up to 2 dimensions, and then of course the diversity is also somewhat limited, or it's like harder for the network to learn much more diverse shapes. It's in theory it would be able to kind of like really kind of like fill the space of possible solutions densely in theory, but in practice probably we would have to go to a higher dimensional modulation space. And then of course also to discover to explore different dissimilarities maybe that use different properties of shapes. I reached the end of the talk. Thanks for the attention, and I'm happy to answer some questions.
Thank you so much, Andreas. Do we have any questions from the audience?
I think Varun may have some questions. He's working on this.
I had a couple of questions. This is Varun from Brown. So one of the questions I had initially was a clarification question, and it relates to the model itself. So if I understand correctly, the model is being trained to learn one geometry at a time, and then you learn the latent representation, and then you modify the latent representation to get new geometries. Is that correct, or am I missing something there? Like for the bracket problem, if you take.
Sorry, you mean for the GIN or for the generative topology optimization part?
The GIN part.
The GIN part, yeah. Sorry, where do I have the slide? Yeah. So the way we do it is like we use this conditional neural field, and we sample, let's say, in one iteration of neural network updates, we sample let's say 9 different modulation vectors and also different coordinates, and we pass them through. So we kind of like train 9 different shapes at the same, or like pass them forward at the same time, and then we kind of like repel them from each other. And since these modulation vectors are like sampled according to a uniform distribution, like if you train it long enough, kind of like you sample the whole space, and then yeah.
Can you say a little more about this modulation space? You said uniform distribution, but you still have to stay around a mean, right? So how do you construct exactly these vectors, the modulation vectors?
Yeah, no, we really I think we also suspect that this is actually helps the structured latent space, but we define a rectangular modulation space between let's say between 0 and 1, but in 2 dimensions, like the square basically, and then we sample uniformly in there. And does it make sense? Yeah.
Why square? Since you have 3, you have 4.
This is just a visualization. so we just have two. So you need to imagine that this is cut off here. So we just have two
Oh,
motivation.
okay, so you have only two. Okay,
Yeah.
okay.
Yeah,
got
yeah,
it.
we have only two.
So,
Yes, yeah.
so it's a hypercube, let's say, in general, and that within
Exactly.
that hypercube. Okay,
Yeah.
but you do have to
yeah.
center that hypercube around the mean, which is the sort of target size.
No, we did not do this. We did not do this. So we suppose that the neural network basically can adjust this in a way that it works out. But it's not necessary to have like the mean, because I mean this is not really interpretable for us, right? It's just some vector. It maps then to a shape. It's not really interpretable. Yeah.
Okay.
Yeah, but it's an interesting question because like this hypercube idea, because you know if we think that since for the hypercubes there's like this diagonal. Sorry if I can. We suspect that if we had not taken a like this square that we sample from, but just a sphere, then we suspect that this could have happened that we don't really see this extremely nice structure, because basically you really try to kind of like along the main diagonals to kind of like make the biggest changes, so to say, make the biggest diversity along the main diagonals. We think this really helps that it's a square. Yeah, but we didn't really do any experiments on it.
Do we have any other questions?
So I have one more question on. So you're looking at the last example, on the stiffness, right? But imagine you're looking at let's say thermal stresses, right? How thermal stresses. So and you have a time-dependent temperature profile, which will give you a time-dependent thermal stress field, and you want to be below a certain point, a certain yield, a certain threshold. So in that case, when you know what I mean, I'm bringing in something that depends on time, let's say cyclic loading, thermal loading, or something like that. What happens in that case? You don't have a static design. You have to sort of, for each case, you have to have the full time-dependent profile, right?
So it's a good question. I mean, if we do topology optimization on this, I guess we still would like to be stable to the most detrimental case, right? To the most to the case that is most damaging, which is probably like having the hottest temperature spikes or something. So this could be one way to modulate it, or like to model it. But if it's time dependent, yes, I'm not really sure how we would do this out of the box. So we have also had a master student who kind of like made certain constraints also varying, which could be viewed as kind of like changing over time. There are different techniques how you could do that. So basically, the way he did it was then to instead of having, sorry, let me just look it up. Oh, yeah. Instead of having let's say a modulation space, then you have also additional inputs that kind of like define the time independence. Like you need to probably condition on time, and then you could model it probably. But I think I would have to thoroughly think it through, and we could follow up if you are interested.
Oh, it's fine. It's a tough problem.
Yeah.
Well, thank you very much, Andreas. It was very clear, and you covered both papers. Very nice.
Thank you so much, Andreas. Do you have any other question? It looks like we do not, so I think that we can stop a bit early today. Thank you so much, Andreas, for your time. It was a really nice presentation, and I think I already told that we should share the video on YouTube. You're good with that, right?
Yes.
Perfect. Okay. Okay. Thank you everyone for your time. Until next week.